look at lesson 9A, and it's focused on measures of central tendency, frequency tables. It's an introduction to statistics overall. We're going to also look at some box and whisker plots, and we're going to talk about sampling techniques a bit. So, measure of central tendency. It's a number used to represent a typical number in the set. So we have our mean, that's our average value. The average bully is kind of mean. So that's the sum of the values divided by the number of values. And then we have our median, that's our middle number. So if I have an odd number of numbers, like this, if I have like 1, 2, 3, 4, 5, this is my median. If I have an even listing of numbers, it would be like 1, 2, 3, 4, 5, 6. So my median would be here in between those two. It's the average of those two, or 3.5. And then mode is our most often number. It is possible for data sets to have no mode if there are no duplicate values throughout a set, or you could even have more than one mode. Bimodal is a common thing. Well, not really common, but it's possible. Once you get into 3 or 4 modes, then it's starting to lose its meaning and it's not as common. And then a measure of dispersion, not technically a measure of central tendency, but it's usually lumped in with it, is the range. And the range is the smallest value subtracting the smallest value. So that is our measures of central tendency. And so first thing, example 1, identify the mean, median, and mode of the data set. Do you notice how I have those numbers all jumbled? First thing I'm going to do is write them from least to greatest. So I'm going to tally them all up. It comes out as 398, which means my mean is going to be 398 over 19, which is the same as 20.947. Oh yeah, the symbol for mean, I should have added it up here, is X bar. Alright, so then to find the median, if I have 19 numbers, that means I should block off 9 on each side. 1, 2, 3, 4, 5, 6, 7, 8, and 9 on both sides. So my median is 19. Our mode, we're going to take a look at our numbers and try and see which one's frequent. So you see there's 2 25s, there's 2 20s, 2 17s, but there's 3 of these 15s. So that is my mode. It's 15. And last but not least, the range. And our range is 36 minus 5, which is 31. So to do a box and whisker plot, it's basically dividing our data set into 4 parts. So we need the second quartile, which is another name for the median. The first quartile, which is the median of the lower half, and the third quartile is the median of the upper half. And you can see there's all of these are marked along our box and whisker. All right. A movie theater recorded the number of tickets sold each showing of a movie during its opening weekend. Obviously not lately. Make a box and whisker plot of the ticket data. So, first of all, I can show you I have my First of all, I'm going to show how to find this sort this data in the calculator. So I'm going to go to Stat Edit and clear out anything that I have in there. And 4, 7, 4, 2, 9. So you can see I've now put all my data in. And I'm going to hit second, quit. And if I hit back to Stat, there underneath Edit, there's 2 of these options here, Sort A and Sort D. So this Sort A, is going to actually sort my values into ascending order. You can use sort D for descending order. So sort A, and then I want to tell it what we want to sort. Well, we want to sort the values in L1 because that's what we just typed in. So sort L1, and to get that L1, it's second one. Then it says done. We'll hit stat, edit, and now you can see I have them from least to greatest, which is really helpful for when you have to find the median or the mean. So, taking a look at this, I have 12 values, so 1, 2, 3, 4, 5, 6. This is the first 6 values. So when I want to find the median, it's going to be so when I want to find the median, I'm going to take a look at median. I have an even number of values here, so my median is going to be the average of these two. So our median is going to be the average of these two middle numbers. So 467 and 469, the average is 468. Then when I go to find the first quartile, I'm actually, since this is not my median, I'm going to include that when I'm trying to find those values. So of here I have 6, so I want the average of these middle ones, the average of 401 and 429, which is 415. The minimum is 302. Then I want the median of this lower half, which will be the average between 499 and 501. 499 and 501. Oh, 504 rather, sorry, is 501.5 for our third quartile. And then we have our max, and our maximum is 746. So this is what's called a 5-number summary. It's outlining from the minimum to the maximum and our 3 quartiles. First quartile, the median, and the third quartile. Now when I go to make a box and whisker plot, I'm going to label an axis, 300, 400, 500, 600. If you were doing it on graph paper, I would make sure I had them the same amount apart, obviously. And then my minimum is right here by 300, 415. So I'm just kind of doing these lines, and then I'll make the whole grid, a box and whisker out of this. And 746. So here's my box, is these quartiles, and then my 2 sets of whiskers, all the way to the minimum and to the maximum. Okay. And box and whiskers are nice for being able to show how wide things are if things are being spread out over a wider disbursement. So an outlier is a data point that is distinctly separate from the rest of the data. If I was looking at this particular set of data, one of them does seem different than the others. Okay, so make your prediction. It's fine. So one definition of an outlier is any data point that is more than 1.5 times the interquartile range, below the first quartile or above the third quartile. Well, first of all, what's an IQR? An IQR, or interquartile range, is our third quartile minus our first quartile. So in this problem, it'd be 501.5 minus 415. Which is 86.5 is our IQR. Now 1.5 times that is 129.75. So anything that is from 415, if I subtract 129.75, I'm down to 285. So anything that was smaller than 285.25 would be an outlier. But there is nothing smaller than that on this set. Now, from our third quartile, 501.5 plus that 129.75, that's talking about like right here-ish. So anything greater than 631.25 would also be an outlier. So in this particular set, 746 is actually considered an outlier. Okay, now again, this particular IQR definition is widely used, but it's not the end-all be-all and the last word in determining whether a given number is an outlier. It's just the strategy that we're highlighting in this particular lesson. So for the data 2, 5, 6, 9, 12, we have the following 5-number summary. Well, our minimum is 2, our maximum is 12, our median is 6, and our first quartile and last quartile are 5 and 9, respectively. Our IQR, or interquartile range, that's 9 minus 5, or 4. Let's see if there's any outliers. It doesn't ask us to do this, but 1.5 times our IQR is 6. So anything that is greater than 15, that's 9 plus 6. So there's no outlier on the top. And anything that is less than negative 1, no outlier. No outlier on the bottom. So this one has no outliers. Alright. So identify any outliers in this data set. Okay, so this is the same data set as we had here. Okay, but I'm going to show you something snazzy with it. So I'm going to take that calculator out again, and I'm going to go up to L1, and I'm going to hit clear on it. So I'm going to hit clear and hit enter. You do not want to go up and hit delete like this, because watch what happens. I lost my L1. And to bring it back, I'm going to hit stat and then number 5. That'll bring it back if you accidentally do that. Okay, so see, now it's back. All right, so I'm going to pause the video and type all of these into L1 for a moment, and I would like you to do the same. So hopefully you've got all of those typed in. It looks like that. I didn't put them in ascending order because I don't need to for what I'm going to do next. So I'm going to go over to stat. I'm going to go over to calculate, and I want this first one, 1 var stats. Okay. So we are working under this one here, 1 var stats. So 1 var stats and hit enter. You can see there's that X bar, or that mean of 20.947. And if I scroll down, there is my 5-number summary right there. So you have your you have your min, your first quartile, median, third quartile, and max. Pretty snazzy. So if we're doing it from here, our interquartile range is 25 minus 15, which is 10. 1.5 times our IQR is going to be 15. So anything that's more than 15 there, so we're talking about more than 25 plus 15 is 40, or smaller than 15 minus 15, which is 0. So this one actually has no outliers. I know, you all thought 5 was going to be an outlier, didn't you? But it actually isn't. So, percentile. It's the value below which a percentage of the data falls. The most common spot that you hear this is like at the doctor's office. You're a certain percentile for height and weight. Okay, so my daughter is at the 25th percentile for her weight. And that just means 25% of the people are lighter than she is. Okay, so if you are the 4th tallest person in the in a group of 20, then 80% of the people are shorter than you and you're the 80th percentile. Okay? So, first thing I want to do is take up my list of numbers and I want to put them in order from least to greatest. This is where that sort A is a really useful feature on the calculator. You don't have to use it though if you don't want to. So, if I want the 30th percentile, now this data set has 20 values in it. It's important for figuring out our 30th percentile. So 30th percentile, or 0.3 of 20, is 6 values. So I want what would have 6 values smaller than it. So 1, 2, 3, 4, 5, 6. So 61 is the 30th percentile. Now for the 60th percentile, that would have 12 values smaller than it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 smaller than it is 82. Notice this is not the 12th value, how it is that there are 12 values that are smaller than it. The other direction we could ask this question is what percentile is 98? Well, 98 is right here, here, and here, but this is the smallest one. So that's the one we're going to focus on because we don't want to have or equal to. We have strictly less than. We want to know how many values are less than it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, 17 values are smaller than it of the 20, which is 85%. So it's the 85th percentile. So suppose we roll 2 dice. What are the different outcomes? Well, the first smallest that the sum of the faces of 2 dice could be is 2. The largest would be 12, right? But are they all equally likely? I have the same chance of rolling a 2 as I do rolling a 7? No. So let's take this a step further. So we have a red die, 1, 2, 3, 4, 5, and 6. I have a blue die, 1, 2, 3, 4, 5, and 6. And I just have some excess. Alright. So I could have snake eyes, 2 ones, and that sum's going to be 2. I could have a 1 and a 2, it'll be 3. Or a 2 and a 1 would also be 3. A 1 and a 3 would give me a 4. A 1 and a 4 would give me 5, 6, and 7. And so I'm just filling in what the sum of the faces would be. Probably seeing a pattern in my numbers by now. And so, yes, my outcomes are from 2 to 12, but you can see in this chart how 7 is the most frequent, and you can see that 7 coming down that diagonal right there. Okay. So, if I wanted what's called a frequency table, it lists the outcome in a sample space and the number of times each outcome occurs. So a frequency table would look like 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And this has a frequency of 1 because there's only one way to get a 2, and only one way to get a 12. 2 ways to get the 3 or the 11, 3 ways to get the 4 or the 10, 4 ways to get the 5 or the 9, 5 ways to get the 6 or the 8, and 6 ways to get the 7. So this is called a frequency table when I have just the sum and the frequency. I could also have a probability table. A probability table, I'm going to add one more line to my table, is saying how likely it is. So this is talking about the theoretical probability. Well, I have 36 different outcomes here on this table. And so my 1 out of 36 is that probability. And this would be 2 out of 36 or 1/18th, 3 out of 36 or 1/12th, 4 out of 36, which is 1/9th, 5 out of 36 doesn't simplify, and 6 out of 36 or 1/6th. Then this would be 1/9th, 1/12th, 1/8, oh, well, whoops, I'm off. I apologize. 5/36th, 1/9th, 1/12th, 1/18th, and 1/36th. Okay, so the first two make a frequency table. This added row is talking about the theoretical probability of each of those events occurring. So, all right, so unfortunately I forgot to ask you for data. So I'm going to say that I sampled a bunch of people at the school and found that of the people I sampled, 2 people had no siblings, 3 people had 1 sibling, 4 people had 2 siblings, 2 people had 3 siblings, and 1 person had 4 or more siblings. So, for a total of 12 people surveyed. Okay, so here I have some experimental probabilities. It's the ratio of the number of times the event occurs to the number of trials. So the probability that of the 12 people I sampled that they have 2 siblings would be 4 out of 12, or 1/3. Probability of 2 to 3 siblings will be probability of 2 siblings plus probability of 3 siblings, which would be 6 out of 12, or 1/2. Probability of at least 1 sibling would be probability of 1 sibling plus probability of 2 siblings plus probability of 3 siblings plus probability of 4 or more. So all of these. So we're talking about 10 out of 12 or 5/6. The other way we could do this is probability 1 minus the probability of no siblings. It's really 1 minus 2/12, which is 10/12. Get to the same place eventually. Just another way of thinking about it. These are all examples of experimental probability rather than the theoretical probability here. Another example of a experimental probability would be if I was rolling the dice from Monopoly and say I rolled the dice 36 times. In theory, I should get 6 sevens, but experimentally, I might get 5 sevens, I might get 4 sevens, I might get 10 sevens. So that's the difference between experimental probability and theoretical probability. So in this particular survey, I took a sample, which is gathering information from only part of a population, right? Because these 12 people that I surveyed obviously are not our entire class, they're not the entire school, they're just not the entire country, they're just a small piece, a small subset. And these sample proportions, they're the ratio of x over n, where x is the number of times that event occurs in a sample size of n. So how many times, and again, it ties right into this experimental probability. Probability of 2 siblings was 4 people had 2 siblings out of the 12 for the whole sample space. So, in a sample of 500 teenagers, 328 had never attended a popular concert. Apparently, they have attended unpopular concerts now. Find the sample proportion for those who have never attended a popular music concert. So, 328 people haven't been to a T Swift concert, over 500. Then I can simplify this, and I can write it like 82 over 125 for a simplified fraction. I could write a decimal. I know, I said it. or I could write it as a percentage. Those are all the same. So one thing to keep in mind whenever I'm doing any type of data collection is that I want to try to avoid any bias. And what do we mean by bias here? We mean anytime a population is either overrepresented or underrepresented in a sample. So if I were to sample our class, I would be overrepresenting freshmen and sophomores and underrepresenting upperclassmen like juniors and seniors. I would also be overrepresenting people who are in honors mathematics and underrepresenting people who are in college prep or regular math. So there's a couple of types of non-probability sampling. So let's say viewers are invited to call into a TV program to express their opinions. This is going to overrepresent or underrepresent certain views, and it's called a self-selected bias. Problem with this is if you have to go out of your way to call into the show, it's going to be based off of that you have a strong opinion, whether it's a positive that you're really pro whatever they're talking about or you're really a negative against what they're talking about. It's a strong response. You also see this type of response on like reviews for a restaurant online, like on a Yelp type of situation, that people go on to those websites to review them have strong opinions. Next one, they surveyed people on the street near the high school. This is called a convenience survey or convenience bias. Since it's convenient for the reporter to stay in one place. Since it's near the school, students or teachers might be overrepresented. So, Mrs. Marhefke decides to select students from her classes, using her judgment of what a typical math student is like. This is called a judgment bias, because one or more experts select a representative sample using their subjective judgments. It is quite unlikely that two experts will agree on what is truly representative. And it's so varied and so biased. So, the New Canaan High School Student Coalition is trying to decide whether to have a band or a DJ for the dance. They decided that each of the committee members should survey the students in their art classes. Identify any bias in this survey method. Well, not everybody takes art. So you're overrepresenting students who are enrolled in art courses and underrepresenting people who may be taking electives in either music or in career and tech ed or anything like foods or anything like that. A better approach would be maybe everyone should survey people in their period 4 class, and then you'll have an equal distribution like that. You'll have some that are art, science, English, or maybe you want to survey everyone in gym classes because it's more you have everyone takes is required to take gym. So all right, so margin of error, that's describing how, and it's an estimate of the error in any sample. When a sample of size n is taken from a large population, the sample proportion has a margin of error of approximately plus or minus 1 over the square root of n. So an opinion poll about the popularity of the town selectman has a margin of error of plus or minus 5%. Estimate the number of people surveyed. Well, 1 over the square root of n is going to equal 0.05. So I'm actually gonna square both sides first. And 0.05 squared is 0.0025. So n comes out as 400 people surveyed. Okay. The survey found that 78% were happy with the town selectman. Use the margin of error to find an interval that is likely to contain the true population proportion. Well, if 78% are happy, but I have a margin of error of plus or minus 5%, that means I could be 5% higher or I could be 5% lower. So we're talking about 73% to 83% is the interval. A survey of 528 high school students, seniors, found that 65% already had a career plans for after high school. Find the margin of error for the sample. Well, it's going to be plus or minus 1 over the square root of 528. So that's talking about plus or minus 0.0435 or 4.35% plus or minus on that. Use the margin of error to find an interval that is likely to contain the true population. Well, from 65%, I want above and below. So 65 minus 4.35% will be 60.65%, and 65 plus 4.35% is going to be 69.35%. So somewhere in that interval. And that concludes our lesson on the Introduction to Statistics.